Okay. So in the last lecture, we have seen the Fourier series for the interval 0 to 2L. Okay. Now we'll see the Fourier series for the interval minus L to L. Okay. So let's have. I will go with the example. Okay. So today we'll solve the examples based on minus L to L. Okay. So we'll have the example. Find the Fourier series for f of x is equal to 2 minus 2 less than or equal to x less than or equal to 0, and this is x 0 less than or equal to x less than or equal to 2. Okay. With period 4. So we go with the solution. Right. F of x is equal to 2 minus 2 less than or equal to x less than or equal to 0, and it's going to be x 0 less than or equal to x less than or equal to 2. Okay. B defined in minus 2 to 2 with period. Okay, so this is what we have. This is the function that we have, and now we want to find the Fourier series in the interval minus L to L. So when we get period is equal to 4, then we have 2L is equal to 4, and hence we get L is equal to 2. Okay, so we got the value of L, and hence we are able to write the Fourier series. But as this interval is minus 2 to 2, so it is in the category of minus L to L, and hence we need to check even or odd function. So what will happen if I replace here minus x, then do I get this x? No, will not get. If I replace here minus x, I will not get this x here because I will get 2. Okay, and so this function is neither even nor odd function. Okay, and if it is neither even nor odd function, then we have to write the Fourier series as. So we can write the Fourier series expansion for f of x is given as. What we'll be having here, f of x is equal to. Okay, so we have to be careful here. What is the formula for the interval minus L to L? Okay, we have the formula f of x is equal to a0 plus summation an cos of n pi x by L plus summation bn sine of n pi x by L. Okay, this is the formula for the interval minus L to L. Okay, and now we know we have calculated the value of L. So value of L is going to be 2 here, and hence we have to modify our formula accordingly. So we have to express this formula with the L is equal to 2. Okay, so what we'll get? We'll get here a0 plus summation n running from 1 to infinity. Then we have an cos of n pi x by 2. Okay, and then plus summation we have n is running from 1 to infinity bn sine of n pi x by 2. That is equation 1. So we can write where a0 is equal to 1 upon 2l. So we get 1 by 4. And we'll be having this is minus 2 to 2 f of x dx. Please be careful for the formulas because if you write the correct formula, then you will get the correct answer. So here the interval is minus 2 to 2, and then we get an is equal to half of integral minus 2 to 2 f of x cos of n pi x by 2, and this is dx. And we have the formula for Bn. Okay, so we'll get Bn is equal to, so it is 1 by L. So value of L is 2 here. The integral from minus 2 to 2 we'll be having f of x and sine of n pi x by 2 x. Okay, so these are the formulas that will have, or this will be the Fourier series for the given function in the interval minus 2 to 2, where L we have replaced by 2. That's why I always calculate this 2L is equal to period and L is equal to, because once you know what is L, you can replace in the formula and then you can write the correct formula. So writing the correct formula is very important, because once you write the correct formula, then your evaluation will be correct. So don't be in hurry to calculate A0, AN and BN. Okay, never start with A0, AN and BN. Okay, because the moment you start with A0, I don't know what will be the Fourier series. So that's why first we have to write the function, then we have to write what is L, and according to L, we have to write the Fourier series. And once you write the Fourier series, then what are these coefficients A0, AN, and BN that we have to consider, and then we have to write the correct formulas for this A0, AN, and BN. And after that, we have to go for evaluation. Okay, so now we have written the correct formula, and so we'll go for the evaluation. Okay, so let us go for evaluation. Remember that what is our function? Our function is f of x is equal to 2 when x is in between minus 2 and 0, and it is x when the value is 0 and 2. So if we want to see the graph of this function, okay, what you will be having the graph. So I'll draw the graph also so you can understand in a better way. Okay, so this function is 2. Okay, from minus 2 to 0, and then from 0 to 2 it is this. So this value is 2. Okay, this is your f of x. I'll use another color. So okay. So we have the function that will be from 0 to 2, and here it will be like this. Okay, so this is f of x from minus 2 to 0, it is 2, and from 0 to 2, it is going to be x. Okay, so simple function. Okay, and now you can see the 0 is a point of discontinuity. So easily we have to break this integral into two parts, minus 2 to 0 and 0 to 2. So we'll evaluate this A0 first. Okay, and hence we consider A0 is equal to 1 by 4 integral minus 2 to 0 f of x dx plus 0 to 2 f of x dx. Okay, and hence what we'll have here, 1 by 4, the integral minus 2 to 0. Okay, the value of the function is 2 dx, and plus 0 to 2, the value of the function is x. So that's what we have here. Now integration is very easy. So let us evaluate 1 by 4. Here we get x minus 2 to 0 plus here we'll get x square by 2 and 0 to 2. Okay, so please be careful for the integration and for the limits. Now let us put, so if I put 0, this will be 0. Minus, because you are using lower limit, so this will become minus minus plus. If you take x is equal to minus 2, then this will be minus 4. Already we are using lower limit, so minus, and this will be plus. Plus, if you put 2, solving this will be 4 by 2, and if you put 0, this will be 0. So what we get here, so we have 1 by 4, 4 plus, this is going to be 2 easily. Okay, and that's why we have here, so 1 by 4, and this is 6. So we get, this is A0. A0 is equal to, we can write 3 by 2. So this is equation 2. I hope this is clear. So no doubt up to yet. Okay. Now we have, okay, so an is equal to 1 half integral minus 2 to 2 f of x uh, cos of please be careful, n pi x by 2 dx. Okay, and as we know the point of discontinuity, so an is equal to half minus 2 to 0. We have here f of x into cos of n pi x by 2 dx plus integral 0 to 2 f of x cos of n pi x by 2 dx. Okay, now we know the values. So here we have half of integral minus 2 to 0, 2 into cos of n pi x by 2 dx plus integral 0 to 2 x into cos of n pi x by 2 dx. Okay, that's what we have here. Now we can see this integral is very easy. So here we need u into v rule. So this is u and this is v. Okay, so we have to use integration by parts rule. This integral is easy, and hence for this integral only we'll use integration by parts rule. So this is an. Then we can say using generalize by parts rule, we get. So what you are able to get is C. An is equal to half of. Okay. Now this 2 remains as it is. Okay. And the integration of this cosine term, so which will be sine of n pi x by 2 upon n pi by 2, and the limits are minus 2 to 0 plus the integration of this now. So x remains as it is. The integration of cosine is sine of n pi x by 2 upon n pi by 2, and now minus the derivative of this x, so it is going to be 1, and the integration of this term, so minus cos of n pi x by 2 upon n pi by 2 bracket square. So please be careful while using the brackets. So here the limits are 0 to 2. Okay. Now let us evaluate this one by one. So what we know is, see, sine 0, 0. If I put minus 2 pi, I'll get sine of minus n pi. Sine of minus theta is minus sine theta, so I'll get sine of n pi. Here, sine of 0 is 0, sine of n pi is 0. Here also sine of 0 is 0, sine of n pi is 0. So this limit vanish, this value vanish at both the limits. This value also vanish at both the limits. So only remaining will be this value. And hence we write since sine of n pi is equal to sine of 0 is equal to 0. So that is the sine terms in curve equation vanish at minus 2, 0 and 2. Okay. Hence we get. So what we are able to get is an is equal to this half will remain as it is and this term so minus minus will become plus. So I'll be having cos of n pi x by 2 upon n pi by 2 bracket square, and here the limit is 0 to 2. So this is the term will be remaining there, and now we have to calculate the limits for this term. Okay, so we get half of we can have this being a constant term, we can take it out, and so we can write it here as this is 2 upon n pi bracket square, and now we have cos of n pi x by 2, and it is 0. So let us apply. So this is half 4 upon n square pi square. Okay. Now apply this 2. So we'll get cos of n pi minus cos of 0. So if you apply 2 here, this 2 will get cancelled and will be having cos of n pi. And then if you apply 0, I'll be having 0 here. So it will be cos of 0. So this is equal to, we can write 2 upon n square pi square. So here this 2 will get cancelled. And now cos of n pi. Okay, so what we know is cos of n pi is equal to minus 1 raised to n, and cos of 0 is equal to 1. So we'll get here minus 1 raised to n minus. Okay, so this is the value of an will have. But now as we know, if we have the term minus 1 raised to n plus or minus 1, then we have to consider what happens if n is even and what happens if n is odd. Okay, so if n is even number, okay, so you can write n is an even, then minus 1 raised to n is equal to 1. So this term goes 1. So this will be 0. So an is equal to 0. Now if n is an odd, then we have minus 1 raised to n is equal to minus 1. And hence we get an is equal to, this will become minus 1, minus 1, minus 1, minus 2. And here we'll get minus 4 upon n square pi square. So this is the next equation 3. Now we have to evaluate what happens to Pn. Okay, so we have Pn is equal to 1 by 2, and we can split this into two parts now. Okay, so we'll have minus 2 to 0 f of x sine of n pi x by 2 dx plus we have 0 to 2 f of x sine of n pi x by 2 dx. Okay, let us write the value of this function f of x. So we get n is equal to half of minus 2 to 0 2 into 2 into sine of n pi x by 2 dx plus 0 to 2. Here we get x into sine of n pi x by 2 dx. Okay, so we got here the value of f of x, and now we know here this integral is easy to calculate, but here we have two different functions. So this we consider here u, and this we consider as v. So for this integral, we have to apply the generalized by parts rule, and hence we apply. So using generalized by parts rule. So we get now we have to apply the generalized by parts rule to this integral. So what we are able to get here, Pn is equal to, this will be half. Now this integral, so it is 2, and we'll be having minus cos of n pi x by 2 upon n pi by 2, and the limits are minus 2 to 0. Plus, for this integral, we have x, and the integration of this sign is minus cos of n pi x by 2 on n pi by 2. Okay. Then minus. So we have to use the derivative of this term. So it will be 1. And here we have the integration of this term. So it will be minus sine of n pi x by 2 upon n pi by 2 bracket square. Here the limits are 0 to 2. Okay. So what we know, the integration or the value of a sine term at both the limit is going to be 0. So we write, since sine of n pi is equal to sine of 0 is equal to 0. That is, the sine terms in both equation vanish at 0 and n. And hence, what we get is, hence, we get, so what will be the remaining part in this equation now? Pn is equal to half of. Okay, this I can write 2 into 2 upon n pi minus I can take half here, and cos of n pi x by 2. Okay, and the limits for this are 0 to, sorry, minus 2 to 0. Now plus, for this, what we'll have, minus, we'll be having 2 upon n pi x cos of n pi x by 2, and the limits for this term are 0 to 2. Okay, so let us apply the limits now, and we can have, this is half of. Okay, so apply the limit. If we put 0, so I'll be having this minus 4 upon n pi as it is. I'll apply the limit for this term only. This is being constant, I have taken it out. So I'll be having cos of 0 minus cos of minus n pi. Okay, because if I use 0 here, this term will be 0, and you are using lower limit, so minus. And if you put minus 2, then this will get cancelled and you will be having minus n pi. Now, for this, so what we can have is this minus 2 upon n pi, we can have common. And here, if I put the value 2, then I'll be having 2 cos of n pi minus 0. Because we have x is equal to 0 here, so this all term will go 0. Now, what we know is since, okay, since we have cos of n pi is equal to minus 1 raised to n, cos of minus n pi is same as cos of n pi, because cos of minus theta is same as cos theta. And then cos of 0 is equal to 1. So using these all values here, we are able to get this Bn is equal to. So what we have here, this is 1 half, and you can have this minus 4 upon n pi. This will be 1 minus minus 1 raised to n, and plus this will be again minus 4. So minus 2 and 2. So it will be minus 4 upon n pi. And this term is minus 1 raised to n. Okay. So that's what we have. Okay. Now simplify this. So what I can do is I can have this minus 4 upon n pi common. So I'll be having this is 1 half into minus 4 upon n pi common. What remains here? 1 minus minus 1 raised to n plus, what is the term you'll be having here? Minus 1 raised to n. So this term will get cancelled. Okay, because we are taking this minus out. So this will become plus, and so this term will get cancelled with this term. So what we get is 1 half into minus 4 upon n pi, and here we'll be having 1. So you can cancel this 2, and you will be having minus 2 upon n pi. So we get Bn is equal to minus 2 upon n pi, and that is the value of Bn. So equation. Now we can see we have got all the values. So we got A0 3 by 2. We got An for odd terms. Okay, and then we have Bn for all the terms. So we can write the Fourier series, and hence we can write from equation 1, 2, 3, and 4 we get. So f of x is equal to p by 2 minus 4 upon pi square summation 1 upon n square cos of n pi x by 2. Please be careful here. This happens only if n is odd. Okay, and minus 2 upon pi n running from 1 to infinity 1 upon n sine of n pi x by 2. Okay, so this is the answer that you will have. So here you need to be careful about this term, because an exists only if n is odd. So we have to be careful here. Okay, here an exists only if n is odd, and so we have to mention it at the last that this term exists. This term is existing if n is odd. So this is how we have to solve the problem based on the interval minus L to L. Okay. So now, do you have any doubt or any question? Yeah, Gaurav has the doubt. Okay. So Gaurav, please unmute yourself and then ask your doubt.
So when do we have to check for even and odd for minus 1 raised to n?
Yes,
For minus 1 raised to n, when do we have to check even and odd condition?
minus 1 raised to n.
Yes.
Okay. So when we have the terms, okay, see, when we have to check that minus 1 raised to n kind of thing, okay. So if you have the term minus 1 raised to n plus or minus 1, or 1 plus or minus 1 raised to n, okay, then only you have to check what happens if n is odd and what happens if n is even. And precisely this term will come if you have cos of n pi or cos of n plus or minus 1 pi. Okay, so when you will have these two terms, this kind of terms will be there. And if you have this kind of terms, any one of this, so it may be minus 1 raised to n plus 1, minus 1 raised to n minus 1, or it is 1 plus minus 1 raised to n, or it is 1 minus minus 1 raised to n. So when you will have this kind of terms, then you have to check what happens if n is even and what happens if n is odd. Okay, because if you write this as it is, then there will be both the terms, existing and non-existing. So what we do is we care about only the existing terms. We do not care about the terms which do not exist. So is that clear, Gaurav?
Yes, sir. Thank you.
Okay, that's good. So if any one of you have any doubt, you can ask. Okay, or shall we go for the next example? We'll go for the next example then. Okay, good. So we'll go for the next example. So we'll have the another example. Obtain the Fourier series expansion for f of x is equal to x square in minus L to L with period L. Okay, so we'll go with the solution. Like f of x is equal to x square be defined in minus L to L with period to L. Okay, so here the clearly interval is minus L to L. So the value of L we don't have to calculate because L is same as L here. And we have to check this is minus L to L. So we have to check whether this function is even or odd. So what do you say? Whether this function will be even or odd function? What do you say? Whether this function is even or odd?
Even.
Now you have to identify it directly. So that f of minus x is equal to f of x or f of minus x is equal to f of minus x. That becomes your rough work. Okay. By looking at the example only, you should able to identify. Yes, you have identified it. That's good. That this function is going to be yes, Nabil. That the function is going to be an even function. So once we know that is going to be an even function, and hence we say the en is going to be 0. Okay. So what we can say directly, the function f of x is an even function. Okay. So please mention if it is even or odd. Okay. Do not mention if it is neither of it. Okay. So we have to mention if it is even or if it is odd. So if it is neither even nor odd, then we don't have to mention. So the function f of x is an even function. And what is the result of the even function? Bn is equal to 0. Okay. So if we know that the function is a even function, then we don't have to calculate Bn. Okay. So directly we can say Bn is equal to 0. And hence what we can write is the Fourier series expansion of f of x is given as having f of x is equal to a0 plus summation an cos of n by x by l. That is equation 1. N is running from 1 to infinity. Now, what is a0 and an here? So, there a0 is equal to 1 upon L 0 to L f of x dx, and an is equal to 2 upon L 0 to L f of x cos of n by x by L and dx. So please be careful while writing the formulas, write proper formulas. And now once you are done with the formula, we are able to evaluate. So first we will evaluate A0. Now consider A0 is equal to 1 upon L 0 to L x square dx. So 1 upon L, the integral will be x cubed by 3 and 0 to L. So 1 upon L, this will be L cubed by 3, and you will have this is minus 0. So one L will get cancelled. So you'll be having L square by 3. So you got A0 is equal to L square by 3. Okay. This is your next equation. Okay. Now once you got A0, the next we have to find is AN. So let us find AN. Okay. So we have AN is equal to. Okay. Think of this. What we'll get here. This is 2 upon L integral 0 to L x square cos of n pi x by L dx. Okay, and as usual we can see there are two functions. So one we assume u, the other we assume v, and then once we have u into v, then we have to use generalized by parts rule for integrating this integral. So we write here using generalized by parts rule we get. Okay, so what we'll get here, see the term. Okay, so we'll get here as Bn is equal to 2 upon L. Sorry, we have An. Okay, so we have An is equal to 2 upon L. Then we have this first term as it is. Now the integration of this. So we'll have sine of n pi x by L upon n pi by L. Now minus the derivative of this term is 2x. Derivative of x square is going to be 2x, and the integration of this term. So we'll be having minus cos of n pi x by L upon n pi by L bracket square. Now plus the derivative of this term. So it is going to be 2, and integration of this. So minus sine of n pi x by L upon n pi by L bracket q. Okay. So we have this is n pi by L bracket q, and we have the limits 0 to L. Now what we know as usual, this sine term is going to be 0, this sine term is going to be 0 at 0 also and at L also. because at L it will become sine of n pi. This will also become sine of n pi. And what we know is, we know since sine of n pi is equal to sine of 0 is equal to 0. That is, the sine terms in above equation vanish at 0 and hence we have, what will be having, we got an is equal to, so this is 2 by L. This minus minus will become plus, so I'll be having L upon n pi bracket square 2x cos of n pi x by L and 0 to a. Okay, so this minus and this minus will become plus, so this I am writing like this. Now let us apply the values. So what will be having, so 2 upon L, this will be L square upon n square pi square. This is 2, and now this constant terms I have taken out. So now what remains here is L into cos of n pi. Okay, and if I put 0, this is going to be 0. Okay, because x will be there, so x is 0, so that means this term is going to be 0. So simplify now, this is equal to this 2 and this 2, I'll be having 4 by L, L square upon n square pi square, and this term, this will be L into minus 1 raised to L. This term is going to be 0. So this L and this L will get cancelled. So what will have, 4 into minus 1 raised to L upon, here I'll be having L square upon n square pi square. Okay, so we get here, that's what you'll be having, this an, and hence we get an is equal to 4 L square minus 1 raised to n upon n square pi square. So this is the value of an we are able to get, equation 3. Now what we have obtained the value of an, we have obtained the value of a0. The function is even, so b1 is equal to 0, and hence we got this a0, we got this an, so we are able to write this Fourier series. Okay, so let us write this Fourier series. Okay, and hence we can write here from equation 1, e, and sorry, we have only 3 equations here. Okay, so we can have and okay, e gate. So what we are able to get is f of x is equal to L square by 3 plus 4L square on n square pi square. We have only pi square is a constant, so this is pi square minus 1 raised to n upon n square cos of n by x by L, and this all terms are existing for all n running from 1 to infinity. Or what we were finding the expansion for x square, so it is L square by 3 plus 4L square on pi square summation n running from 1 to infinity minus 1 raised to n upon n square cos of n pi x by L. So this is what the Fourier series will have for the even function in this interval minus L to L. Okay. So do you have any doubt in this example, or do you have any doubt up to it? Okay. That's great. You don't have any doubt this example. Okay. Now, no problem. So we are able to solve the example based on 0 to 2 pi. We have seen the interval from minus pi to pi. So in this interval minus pi to pi, we have seen what happens to the even function, what happens to the odd function, and now after that we have seen the interval 0 to 2L. Okay, and then we have also calculated the Fourier series expansion in this interval 0 to 2L. Now we have seen the interval minus L to L. So if we have the function which is neither even nor odd, then we have to find out all A0, AN and PN. If we know the interval is minus pi to pi or minus L to L, and we know about the function that it is even, then we can write directly that the Pn is going to be 0, and we have to calculate only A0 and An. And now, if we know the function is an odd function, then we have A0 equal to 0, An equal to 0, and we have to calculate only Pn. Okay, so this way we are able to find out the Fourier series expansion in all different intervals. Okay, and now if we are forced to find the Fourier series in only sine function or in only cosine function, so that we have to see. Okay, so Dipesh said even or Fourier transform. Okay,